Welcome to this session. Today we are going to discuss question bank problems in module 4. There is recurrence relations. Now here, whenever any recurrence relation will be there, suppose if I am going to consider a second order or third order or any order recurrence relation will be there, then the recurrence relation is Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 and so on. If it is there, then such a linear equation we can call it as a nth order linear equation. Now, if I am going to restrict only up to Cn minus 2 an minus 2, then we are going to consider a second order linear recurrence relation. Suppose if I am going to consider up to Cn minus 3 an minus 3, then it is nothing but a third order recurrence relation. Suppose if I am taking Cn an plus Cn minus 1 an minus 1 and plus Cn minus 3 and an minus 3 equals to 0 if I am considering. This is the third order linear recurrence relation. Now, the right hand side, if I am going to consider it as 0, then it is a homogeneous, otherwise it is a non-homogeneous. So here we are considering up to an minus 2 for n is greater than or equals to 2. So this is recurrence relation is known as a second order homogeneous recurrence relation. So here C1, C2, Cn, Cn minus 1, Cn minus 2 are all real constants provided that Cn is not equals to 0. If any equation which is of this form, recurrence relation which is of this form, in order to find the solution, first of all we are going to find the auxiliary equation. So for that we are going to find, let us assume that the solution of the equation 1 which is of the form an is equals to k c k to the power of n. In the same way, an minus 1, if I am going to consider this is a c k n minus 1, and an minus 2 if we are going to consider c k to the power of n minus 2. So now we are going to substitute in the equation 1. So equation 1 will become c k to the power of n, and of course cn will be there, and an this is going to be replaced, and plus cn minus 1, an minus 1 is replaced with c k to the power of n minus 1 plus cn minus 2, an minus 2 is replaced with c k to the power of n minus 2 equals to 0. Now, if I am going to take c k to the power of n minus 2 as common, then this is cn k square plus cn minus 1 k into k to the power of n minus 2 is nothing but k to the power of n minus 1 plus cn minus 2 equals to 0. Here the thing is either this is equals to 0 or this is equals to 0. So here if k to the power of n minus 2 is not equals to 0, because we are assuming the solution which is of this form, so there is no question of becoming 0, then we are having the another one is cn k square plus cn minus 1k plus cn minus 2 is equals to 0. This equation is known as the auxiliary equation. The auxiliary equation or characteristic equation of equation 1. So we are going to find the solutions for the any recurrence relation. First of all, we are going to find the auxiliary equation and our characteristic equation of the given recurrence relation. Then after that we are going to find the roots for the auxiliary equation. Then the roots are, there are three possible cases will be there. The roots are real and distinct, and the roots are real and repeated, and the roots are imaginary roots or complex roots. These are the three possibilities will be there. So roots of the auxiliary equation, one is real and distinct, and another one is real and repeated. real and repeated. Another one is roots are complex roots. So these are the three different possibilities will be there. In these three different possibilities, whenever the roots will be there, then how to find the solution? How to find the solution? So for that, whenever real and distinct roots, let us say that k1 and k2 are distinct roots, then the solution is this. An is equals to a k1 to the power of n plus b k2 to the power of n. So here a and b are arbitrary constants. Suppose if we have k1 and k2 are real roots, then the real roots are repeated, then the solution is an is equals to a plus bn k to the power of n. A plus bn k to the power of n, and a and b are the arbitrary constants. And the third case, case 3, if k1 and k2 are complex roots, then one is a conjugate of the other. So k1, if I am taking in the form p plus iq, k2 is another k2 which is definitely in the form p minus iq. In such case, we are going to write the solution an is equals to r to the power of n, a cos n theta, b sin n theta, and where r is equals to modulus of k1 or modulus of k2, which is nothing but square root of p square plus q square, and theta, we are going to find out what is r power n. R power n is nothing but by using this, and theta by using this we are going to calculate theta value. Then if you are going to substitute in the expression, then simultaneously we are going to find the solution for the homogeneous equation. Now let us go for one problem. So here solve the recurrence relation an minus 4an minus 1 plus 4a into. So this is a second order recurrence relation, and here it is given what is a naught will be given and a1 is given. Now we have to find what is the solution for this recurrence relation. So for that, and once again the auxiliary equation if you are going to calculate, then this is once again the same procedure like the earlier. Whatever the procedure will be there, the same procedure we are going to adopt. That is an is equals to c k square k to the power of n be the solution. Then we are going to get this is the auxiliary equation. Now we are going to write the same thing as here. So what is the auxiliary equation is cn k square plus cn minus 1 k plus cn minus 2. This is the auxiliary equation. So here cn is nothing but an coefficient, and next cn minus 1 is nothing but see what is the standard form? It is nothing but cn an plus cn minus 1 an minus 1 plus cn minus 2 an minus 2. This is the standard form. So here cn is nothing but the quotient of a1. So cn is equals to 1. Similarly, cn minus 1 is equals to minus 4. Similarly, cn minus 2 is nothing but 4. So if I am going to substitute, then this will become k square, and next minus 4k, and next plus 4 is equals to 0. Now this, if you are going to find the solutions for this is nothing but k minus 2 whole square equals to 0, which is equals to k is equals to 2. So here the real root 2 is a real and it is repeated. So the solution is nothing but we are going to write it as an is equals to a and k1 to the power of repeated root. So whenever the roots are repeated, it comes under case 2, a plus bn into k to the power of n. So here a plus bn into k to the power of n. K to the power of n is 2 to the power of n. So now a and b are constants. Now we are going to find what are the a and b values. So for that, if I am going to substitute n is equals to 0, then we are going to have a naught is equals to a plus b into 0, then 2 to the power of 0, which implies a is equal to a naught and a naught is equals to 5 by 2. A naught is equals to 5 by 2. And similarly, n is equals to 1 if I am taking, then a1 is equals to A plus B into 2. So which is equals to A1 is nothing but 8. 8 is equals to A plus B. This is A naught is equals to, what is A naught is 5 by 2. So A is equals to 5 by 2. Now A is equals to 5 by 2, then I am going to substitute. This is 8 minus A is equals to B, which implies B equals to 8 minus 5 by 2. Subsequently, 11 by 2 we are going to get. Subsequently, A is equals to, we have A plus B into 2 will be there, right? A plus B into 2 will be there. So I am going to have, this will be 4, this will be 4. So it is nothing but 4. Then it is 4, 8 minus 5. It is 3 by 2. It is 3 by 2. So now A is, we are having 5 by 2 and B is equals to 3 by 2. Then equation 1 will become, AN is equals to, A is equals to 5 by 2 plus B is 3 by 2 into N into to the power of N. So this is the solution for the given recurrence relation. Now, another one is solve the recurrence relation. This is nothing but the third order recurrence relation, because here Cn is equals to 1 and Cn minus 1 is 0 and Cn minus 2 is 0, Cn minus 3 is 1. Now, the auxiliary equation is nothing but just we have to consider like the previous one, Cn k square. Our auxiliary equation is Cn k square. From there we have to write. Here we are going to write Cn k cubed because it is the third order recurrence relation, plus Cn minus 1 k square plus Cn minus 2 k plus Cn minus 3 is equal to 0. Now we are going to substitute in this. The values is k cubed plus 0 plus 0 plus 1 equals to 0. So we are having k cubed plus 1 equals to 0. So k cubed plus 1 is equals to 0. Then we are going to find the roots of this auxiliary equation. So this is directly we are writing the auxiliary equation. Then the roots of the auxiliary equation by trial and error method, if k equal to minus 1, then this is going to be satisfied. So we can say that minus 1 is one root by using synthetic division. So k cubed term, k square term, k term and the constant term. Then we are going to take it as minus 1, 0, 1, then minus 1, plus 1, 1, minus 1, this will become 0. So this will become, this equation can be written as k plus 1 and the next one is k square minus k plus 1 equals to 0. So it is k plus 1 equals to 0, then k square minus k plus 1 equals to 0. So then k equals to minus 1, then it is minus b plus or minus. So it is minus b plus or minus root b square minus 4ac by 2a. So we are going to have like this. So it is nothing but 1 plus or minus root 3i by 2. Root 3i by 2. So here, here the roots are, one root is real and the remaining two roots are complex roots. Now we are going to find the solution for this. So for that, I am going to write the solution is an is equals to a and next k1 k to the power of k1 to the power of n. So it is nothing but minus 1 to the power of n plus, and another one is r to the power of n and then b cos n theta and plus c sin n theta. Sin n theta. Let us take the constants are b cos n theta plus c sin n theta. Now here we are going to find what is r value and what is the theta value. What is the theta value? So this is the solution where r is equals to, what is r is equals to, we are going to write it as p plus iq or p minus iq. So which is equals to, then it is r is nothing but we are going to have, this is K1, and which is equals to K2, which is equals to square root of P square plus Q square. Then we are having like this. Then what is the P square is? Then here what I am going to take it as K2 as 1 plus root 3 by root 3I by 2. And so here I am going to write 1 plus 2 plus root 3 by 2I. So this is 1. And K3 if I am going to consider 1 by 2 minus root 3 by 2I. So P plus IQ, P minus IQ. So which is nothing but P square plus Q square, which is nothing but 1 by 4 plus 3 by 4 under square root. So it is nothing but 1. I am going to get R is equals to 1. And theta is equals to tan inverse Q by P. So which is nothing but tan inverse Q is equals to, so root 3 by 2 by 1 by 2. So which is nothing but tan inverse root 3. Tan inverse root 3. So which is nothing but pi by 3. Pi by 3. So the solution, we are going to write the solution as an is equals to a minus 1 to the power of n plus r is nothing but 1 to the power of n is nothing but 1. So then it is b cos n theta, and theta is equals to pi by 3. So n pi by 3 plus c sin n pi by 3. So this is the solution for the given recurrence relation. Now the third one, if we are going to consider the third one in the same order, in the same way, so we are having just I'm going to get, this is let us an plus 2 and plus 3an plus 1 and plus 2an minus 3an is equals to 0. Just we are going to take this as this side. So an plus 2 and plus 3an plus 1 and plus minus an which is equals to 0, and this is for n is greater than or equals to 0. So we are going to substitute, put n is equals to n minus 2. So then this will become an plus 3an minus 1, then and minus an minus 2, which is equals to 0. Then n is equals to n minus 2. Subsequently, n is greater than or equals to 2. N is greater than or equals to 2. So the given equation we are going to write in this form, and we are going to apply the auxiliary equation for this, which is similar to the earlier one. So it is nothing but Cn, this is a Cn k square plus Cn minus 1 k and plus Cn minus 2, which is equals to 0. Now this is Cn is nothing but the quotient of an, so which is 1. So k square plus 3k, and next another one is minus 1. So because Cn minus 2 is minus 1, so we are having the solution is of this form. So it is nothing but k square and plus 3k minus 1 will be the solution for this, and for the recurrence relation for this. Now we are going to find the roots for this recurrence relation. So now the roots for this recurrence relation is minus b plus or minus b square minus 4ac. So it is nothing but plus 4 by 2. So this is nothing but minus 3 plus or minus root 13 by 2. So which will be minus 3 plus root 13 by 2 and minus 3 minus root 13 by 2. Root 13 by 2. So these are the two roots will be there. Two roots are real and distinct. Two roots are real and distinct. So let us, I am going to take this as k1 and this as k2. Then the solution is, an is equals to a k1 to the power of n. So it is nothing but minus 3 plus root 13 by 2 whole to the power of n plus b and next minus 3 minus root 13 by 2 whole to the power of n. So now we are going to find a and b values by substituting this n is equals to 0. We are going to get a naught is equals to a into minus 3 plus root 13 by 2 and plus b into minus 3 minus root 13 by 2 whole to the power of 0, whole to the power of 0. Subsequently, a naught is equals to 3, then we are going to get a plus b. So let us have, this is a one equation and the solution, which is nothing but this, we are calling it as equation 1, and then I am going to call it as equation 2. Then once again n is equal to 1 if I am going to substitute, then I came to know what is a1. a1 is minus 3 plus root 13 by 2 whole to the power of 1 plus b into minus 3 minus root 13 by 2 whole to the power of 1. And here this will become a1 is 1 and it is nothing but 2. I am just taking to 2 this side. So a into minus 3 plus root 13 and next plus b into minus 3 plus minus root 13. So now this is equation 3. If I am going to solve equation 2 and equation 3, subsequently we came to know what is a and b values. After getting a and b values, we are going to substitute in this expression like the previous problems. Then we are going to get the final solution. Now suppose the given equation, which is of the so far whatever we have discussed, the homogeneous, that means f of n is equals to 0. Now f of n is not equals to 0. F of n is not equals to 0. Then we are going to find a solution. So whenever f of n is not equal to 0, then we are going to call it as a non-homogeneous recurrence relation. Non-homogeneous recurrence relation. So to find a non-homogeneous recurrence relation, we have to find a solution in such a way that we are going to find a solution for the homogeneous and a solution for the non-homogeneous. So it is nothing but an is an power h and an power p. And an power h, we already know how to find out that. That means we are going to find the homogeneous solution is nothing but an power h. Now we are going to find what is it, how to find the solution for an power p. an power p. So here, for finding the solutions for particular integral, particular solution, there are the three different cases will be there. So here, f of n is a polynomial of degree q. The right hand side, f of n is a polynomial of degree q, and 1 is not root of the characteristic equation. Then the assumed particular integral is this. The assumed particular integral is this. Then we are going to find out what is a0, a1 and so on, an. After that we are going to substitute in that expression. So then we came to know what is an to the power of p. And similarly, this is true whenever f of n is a polynomial of degree q, and 1 is not root of the auxiliary equation. Suppose if it is a polynomial, second case is f of n is a polynomial of degree q and 1 is a root of the auxiliary equation, and that is nothing but it is going to be repeated m times. It is going to be repeated m times. So 1 is repeated m times. Then what is the solution? What is the particular integral? So particular integral, whatever the earlier will be there, the same thing into if it is repeated m times, then n to the power of m we have to take. Suppose if 1 is the root of the auxiliary equation, it is repeated twice only, then we are going to write it as n square. If it is repeated thrice, then we are going to write it as m cubed. Like that. If it is repeated m times, then we are going to write the assumed particular integral as n power m into the whole thing. And now, suppose the third case is, if it is not a polynomial, f of n which is of this form, alpha b to the power of m, where alpha is a constant and b is not root of the auxiliary equation. Then the particular equation is b is not root of the auxiliary equation. Then the particular integral is this is. Suppose if we are going to find this is for b is not root of the auxiliary equation. Suppose b is root of the auxiliary equation, and if it is repeated m times, then we are going to multiply whatever the previous one. So a naught b to the power of n, then b to the power of n, that is going to be multiplied with n to the power of m. So which is similar to the previous one. So these are the assumed particular integrals. So whenever f of n, which is either the first form or one is not root of the auxiliary equation, and case 2 is f of n is a polynomial and 1 is the root of the auxiliary equation. If it is repeated m times, then what is the particular integral? And then f of n is equals to a specific form alpha b to the power of n. Then how we are going to assume a particular integral? And then if b is not the auxiliary equation, so if b is the root of the auxiliary equation which is repeated m times, then what is the assumed particular integral? Then this is the way that we are going to find out the assumed particular integrals, and then we are going to find out this. So here let us consider it is a non-homogeneous recurrence relation will be there, and to solve this non-homogeneous recurrence relation, then first of all we are going to find the solution for the homogeneous equation. So for the homogeneous equation, we first will make it as 0. Then we are going to write the auxiliary equation as k square plus 4k plus 4 equal to 0. Then the roots of this is k plus 2 whole square equals to 0. So k equals to minus 2 are the roots. Whenever minus 2 is a repeated root, then obviously we are going to write this a(n) power h as then a plus bn, and next k1 to the power of n. What is k1 to the power of n? Minus 2 to the power of n. So this is the solution for the homogeneous equation. Now we are going to find out the solution for the non-homogeneous equation. So for that, we are finding the assumed particular integral. Now let us go for the right hand side. Right hand side is nothing but a f of n is a polynomial of degree 0. And moreover, the 1 is not root of the auxiliary equation. So whenever if 1 is not root of the auxiliary equation, then q is a polynomial of degree q. So here polynomial of degree 0. So if it is a polynomial of degree q, up to here we are going to consider. If it is a polynomial of degree 1, up to here we have to consider. If it is a polynomial of degree 2, up to here we have to consider, like that. So if it is a polynomial of degree 0, then we have to consider up to here only. So polynomial of degree 1 up to here, polynomial of degree 2 up to here, polynomial of degree 3 up to here, polynomial degree q up to here we have to consider. So here it is a polynomial of degree 0. So we are going to write the assumed particular integral as only a naught. Now, whenever if I am going to say that it is the solution for the given equation, right? It is a particular integral for the given equation, means it is automatically satisfies the given equation. So, what is a n minus 1 power p, which is also a naught, and a n minus 2 whole power p, which is also a naught. Now, what we are going to have, equation a will become a naught plus 4a naught, and next plus 4a naught is equals to 8. Then this will become 9a naught is equals to 8. So now a naught is equals to 8 by 9. A naught is equals to 8 by 9. So then the particular integral is the assumed particular solution as a(n) power p is equals to 8 by 9. So now this is called equation 2. Now the solution for the given non-homogeneous equation is a(n) power h plus a(n) power p. Then we are going to add these two. So it is nothing but a plus bn and minus 2 to the power of n, and next plus 8 by 9. So this is the solution and for the non-homogeneous recurrence relation, but the conditions are given. with the help of these conditions, we are going to find out what is the A and B values. So if n is equal to 0, then A naught is equals to A, and this will be 1, so plus 8 by 9. This is minus 2 to the power of 0 is 1, B is 0. So we are having A naught is given already, it is 1 is equals to A plus 8 by 9. So then A is equals to 1 minus 8 by 9. So it is 1 by 9. 1 by 9 is A. Similarly, n is equal to 1 if I am going to consider A1 is equals to A plus B, and it is minus 2 plus 8 by 9. So now A1 is equals to 2. So it is 2 equals to A plus B minus 2 and B is of course it is okay, then plus 8 by 9. So dividing throughout the equation with 2, then I am going to get 1, then it is A plus B, and this is minus of, then it is 4 by 9. So then if I am going to substitute, this is minus of A plus B, which is equals to 1 minus 4 by 9. Subsequently, if I am going to substitute, and A value, if I am going to substitute here, this is 5 by 4 I am going to get, then A is equals to, this is similarly this I am going to write A plus B is equal to minus 5 by 4, and A value if I am going to substitute as 1 by 9 plus B is equal to minus 5 by 4, then B equals to minus 5 by 4 minus 1 by 9. So I am going to get B value here, and of course I am going to get A value here. Both values we are going to substitute in this expression. Then we came to know that is the final solution. That is the final solution. So in this way, we are going to find out any particular solution will be there. Then how to find out non-homogeneous recurrence relation will be there. Then how to find out a solution for that. And suppose here, find a recurrence relation by using a substitution method. By using a substitution, where sequence is given. So for that sequence, we are going to find a recurrence relation. Now, so far we are going to solve a recurrence relation. Now we are going to find a recurrence relation for the given sequence. So whatever the sequence will be there, this is A0, this is A1, this is A2, this is A3, and so on. Sequence is nothing but the arranging the numbers. The numbers are in a particular order, particular fashion. So that is going to be arranged in a particular order. So that is known as a sequence. Now here, A0 is equals to 0 will be there, A1 is equals to 2 will be there. Now I am going to write what is the relationship between the difference of, say there is a particular relation will be there. So that numbers are, we are calling it as a sequence. So what is that relation? If I am going to find that relation is known as a recurrence relation. Recurrence relation is nothing but the successive two terms relation. How they are going to depend. So that relation is known as a recurrence relation. That we are going to find out. Now, A1 minus A0. A1 is given and A1 is given. So that I am going to get A1 minus A0 equals to 2. So it is nothing but 2 into 1. And A2 is given. Once again, A2 is 6. Now I am going to find out A1 minus A0 I find out. Next, A2 minus A1. So I am going to get 4. That is going to be written like this, 2 into 2. Next, A3 will be there. Now A3 minus A2. So 6 I am going to write. 6 can be written as 2 into 3. Then A4 minus A3. Then A5 minus A4, A6 minus A4, like that. So just to observe this, all the things. So what is that? The relation between the two successive, the difference between the two successive terms. So an minus 1 is equals to, see, observe this, 2 will be there, 1, 2, 3 and so on, 1, 2, 3 and so on. It will be continuously, it will be continued up to, see here, A6 term we are going to calculate up to 6. A5 term will be there up to 5. A4 term will be there up to 4. Now we have the nth term, so I am going to write 2 into n. So this is nothing but a recurrence relation. So we are just finding the recurrence relation whenever the sequence is given. Whenever the sequence is given, now with that sequence, we find what is the recurrence relation. So these are the few problems which are there in the recurrence relations, and here some problems only we solved. This is only first order because an minus 1 will be there. So up to an minus 1 means it is a first order recurrence relation. If an minus 2 will be there, then we are considering up to an minus 2, it will be second order. Up to an minus 3 will be there, it is third order, and so on it will be there, and so on it will be there. So with this I conclude this. These are the few problems from the question bank. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.